So these circuits and analysing circuits using these things called Laplace transforms. That's what it's about today. What are they? What are they used for? And how do we use them? We're going to look at a circuit. We're going to start off with more straightforward circuits than this, but we're going to end up hopefully looking at the idea of a circuit involving L, R and C. Not what happens in a circuit like this if we have, initially anyway, if we have a continuous AC supply connected to it. What we're interested in is what happens if we connect components like these, an inductor, or a resistor or a capacitor, to a step voltage, a DC voltage, so stepping up to 4 volts. Or if we gradually increase the voltage up to a fixed value, so it starts at 0, ramps up to something like 10 volts, something like that, and then goes flat. We're not going to concentrate initially on what happens in an AC circuit. Now, if I were to step voltage this, put a step voltage across a circuit like this, or in this situation, if I had a charged capacitor, so a capacitor was initially charged, and then I close this switch, something will happen in the circuit before it drops down to a steady state. And that period of time during which we're waiting for a circuit to settle down to a steady state is called the transient period. And what we're after doing is finding out what happens to this circuit during that transient period. Transient doesn't mean uninteresting or irrelevant. It can have a quite significant effect. When you turn off or turn on a circuit, that can be quite a dangerous time for delicate components, for example. So it might very well be important to know what happens during the initial transient period when you turn a circuit on. And that's what we're going to focus on. Here is a circuit that sort of models that. So we've got an LRC circuit, and we're going to try and model this during the transient period when I switch this circuit down. I don't know what I've said in here. Now, I haven't actually explicitly said, but this capacitor is initially charged. So this is a charged capacitor. Initially charged. Oh, does it? Right, okay. Fair enough. Just as well I did it with the magic pen. So, what do you think will happen when I switch this circuit on? I'll put a set of axes here. What I want you to do to try is to sketch what you think will happen when I turn on the supply into a circuit like that with a capacitor initially charged. And then we'll look back at the end when we've analysed this circuit and see, well, whether or not your sketch is anything like appropriate. So, what's this mathematical model going to be then? A mathematical model that involves a change. Think about this for a minute. We turn this circuit on. Things are changing. If we look back at the circuit, then I would imagine as soon as I turn the circuit on, this capacitor is going to start to just discharge. So things are going to change. The voltage share across each of the components in this circuit is going to change. Before I turn on the switch, what do you think the voltage might be across the capacitor? What do you think the voltage might be across the resistor and the inductor? If I were to measure them. Across what? Across the capacitor, right. So if I put the CRO across the resistor or the inductor initially, before I turn on the circuit, what would be? Right, probably 0, wouldn't it? Everything's across the capacitor. As soon as I switch this switch, then things are going to change, aren't they? So our model involves changes. And that involves solving something called a differential equation. And in our maths, we're going to start looking at other ways of solving differential equations. One way of solving differential equations is to use the Laplace transforms. For this circuit, this is the differential equation. And I want to have a look at this for a second on the next sheet that you've got. Let's look at this and compare this with the circuit. So I'm going to be switching backwards and forwards between these slides. You might want to have this page available as well as the one we're looking at now. This term here is to do with inductor. The clue is in the L that's here. If we look back at our circuit, and with the inductor in the circuit, then I know that the voltage, by the way, each of the terms in here is describing the voltage across the inductor. So this is the term for the voltage across the inductor. This is the term for the voltage across the resistor and voltage across the capacitor. Well, let's start with this one. The voltage across the capacitor is given by the charge over the capacitance, Q over C. If we think about the resistor, the voltage is IR, V equals IR. This is the interesting bit. Is that current? A Q by dt. A Q is charge. Think about what we mean by a differential. Does dq by dt mean current? If I differentiate something, it tells me the rate of change of. The rate of change of charge with time. Is that what we mean by current? Yeah. The flow of charge. The rate of change, the flow of charge is what we mean by current. So this, in all but name, is IR. I dq by dt times the resistance. So that's just another way of writing Ohm's law for the voltage across the resistor. How do I get the voltage across an inductor? It's the inductance times the rate of change of current, if you remember. Well, the rate of change of current is dq by dt, so actually the rate of change of current turns out to be the second differential of charge with time, the differential of the differential. And so this is the term to describe the voltage across the inductor. This is the term to describe the voltage across the resistor and the voltage across the capacitor. It's a differential equation. Equals naught. Why does it equal naught? Sorry? Right, there's no supply voltage, so if I added all the voltage across the components, they should add up to be 0. So the total voltage is going to be 0.
Be careful. They'll all, voltage,
yeah.
They'll always, the sum of those three voltages to any number.
So that differential equation is what we've got. And we're going to be looking at other ways of solving differential equations like this, but we're going to focus on the Laplace way of doing it. Well, I'm not going to do it now, because that's for later. The solution to this second order differential equation, and it's by the way called a second order because it's got a second differential in it here, describes how the charge varies with time in this circuit. We're going to use the Laplace transforms to find that solution. And if I flip over here, I've actually got the solution here. The solution for that equation is this. The charge equals the initial charge times e to the minus alpha t, where alpha is some constant, cos omega t plus alpha over omega sine omega t, where omega is the angular velocity related to the frequency of the circuit. This I could have put in a t, because it's the instantaneous charge at any time t. So if I want to know what is the charge at any point on here in this circuit, then that's the formula. If, for large values of t, then e to the minus alpha t is 1 over e to the alpha t. And as that tends towards a large value, then this becomes, why have I put 1? That tends towards 0, doesn't it? That should be a 0 here. Just change that on the notes. So if we leave the circuit for long enough, the charge will fall to 0. The capacitor becomes finally discharged. But if we plot that function, we get this. So it drops to 0. And this is the circuit. This is what you might have sketched if you thought about it in this circuit. It's an oscillating change. The voltage across the capacitor oscillates, positive, negative, and dies down to 0. We can think about some of the values that are on here. We've got an initial value there of about 1 point something, and we could work out what that is, because if this is the charge, and I'm just hesitating because I've put charge in here or voltage. Let's look back at the original circuit. Did I get any values in there? No, I haven't got any values in there, so I think to plot the graph I'll put some values for L, R and C in, so you won't be able to put any values on your curve, but that might be the shape that you expected to see. So for given values of L, R and C, I can predict a few things about this circuit. I can predict what the initial voltage might be across the resistor, if that's what I was interested in, or across any of the components in there. I could predict how long it would take before the charge or the flow dropped to 0. In other words, before I got to a steady state in the circuit. So if we can come up with an equation that describes a circuit, and that's what this is about really today, coming up with a model to describe a circuit, then we can say what's going on during this transient period. This describes what happens to the circuit during a transient period. How do we get from the ordinary differential equation to the solution? We use these things called Laplace transforms. And generally, solving ordinary differential equations involves integration. Integration techniques involve trying to get an integral to look like a standard integral in a table. We've talked about that. We've got tables of standard integrals. Laplace transforms is an extension of this. We use a table of transforms to try and get from one state to another. And that's this table that I've given you here. So that was a little introduction, sort of the idea of Laplace transforms. What I want to do now is to go back a step and start off with really straightforward circuits and build up these ideas so we can build our own models for these circuits.